Yeah, I come from the nuclear spectroscopy background. So most of my work is in intradisciplinary, means development of materials and evaluation with the spectroscopic technique. But then it was my research topic, and then later on I moved into industry, and I have experience of developing around 80 different kind of devices. So I came here with my presentation, but then after coming here, I could sense that the most of the people here are from IT and this thing, AI and computer science background. But then maybe it's an opportunity for me and opportunity for you people, like applying AI to the machines, or maybe for me it's knowing new things in computer. So that is how we will go ahead. So I'm at present I'm working in Gujarat, this thing, MSA Gujarat Molecular Imaging India Private Limited. Now this MSA stands for Muni Seva Ashram. So Muni Seva Ashram is the place near to Wagodia, and it's a hospital, cancer hospital. And in the cancer hospital campus itself, there is a manufacturing plant of this thing, cancer diagnostic drug. So at present, I am associated with that plant, and we manufacture radioactive tracer, PET tracer. So it is positron annihilation tomography. It is used for cancer diagnostic. So that we are making. Yeah. So in this thing, MSC Gujarat, we manufacture basically FDG. FDG stands for fluoridated glucose. So basically, it's a glucose molecule, and in the chain of glucose, we stitch radioactive fluorine. So in our plant basically works, there are different work. First task is creating fluorine isotope, radioactive isotope. So that happens with irradiation of oxygen 18 molecule with cyclotron. So we have a cyclotron facility, and it's a 18 million electron volt this thing proton beam line. So first in our plant we irradiate oxygen molecule with proton, and then oxygen nucleus gets converted into fluorine, and then after the fluorine we from cyclotron this thing liquid target we transfer to the hot cell. So hot cell is the this thing guarded area, basically a guarded area. It is lead shielded environment where radioactive fluorine molecule is transferred, and then in the hot cell there is a arrangement of synthesizer. So synthesizer is basically automated machine in which we have to put the reagents for synthesis of glucose. So and the synthesizer operate from outside, it is operated, and then a synthesizer synthesize the fluoridated glucose, and then it transfers into dispensing area. So dispenser is also a guarded area basically, because we are dealing with radioactive medicine, and once means daily we produce around 20 curie activity, and anything about 100 millicurie is a human hazard. So most of the operation is unmanned in, and it is automatic. So in dispenser, once we transfer the medicine, we dispense the known quantity as per the order of hospital. We dispense the quantity, and then it is automatically the ampule is sealed and then transfer into lead bottle, and then transported by road or by air to the client end. That is how we operate. And this talks about the plant operation. And in this radioactive plant, all our machines are from abroad. Means the cyclotron machine is made by Ion Beam Application Lab, Belgium, IBA. The hot cell and dispenser are made by Comesser, this thing, Italy. And all the machines are automated. But then we are operating this plant at Muniseva Ashram. But then at the time of Corona, there were no support from our foreign principal. So, and they were supporting through this thing, tele support, and no physical, no anybody was ready to come or help us. And there was shortage of parts and everything. So in this plant, we started developing. We are too much dependent on these people, and it is difficult to this thing sustain this plant, cyclotron plant. That is how we started development, and we developed many parts of cyclotron. Cyclotron is made by IBA Belgium, but many parts of cyclotron we develop ourselves, like ion source. Ion source is basically a plasma, hydrogen plasma torch, which generate proton beam. So that we develop at our end. Like other thing, like target. So target is basically where nuclear reaction happens between proton beam and this thing, oxygen, O18 isotope. So it's a place where actual nuclear reaction happens, and means it involves lots of heat. Means while proton this thing react with the oxygen nucleus, lot of heat is generated. So there is a arrangement of typical, there is a helium flow and water flow channels and everything. So that liquid targets we develop by our own. In addition to that, in our plant, means at present we are manufacturing FDG. FDG is fluoridated glucose, but it is medicine for diagnostic of general medicine for diagnostic of and scanning of whole body. But nowadays there are this thing, certain medicines, means organ specific medicine comes, like F-DOPA. Now F-DOPA is dopamine, and we know that our mind means mind functions are on the basis of dopamine. So F-dopamine, if we inject F-dopamine, we can get very good scan of brain. Like there is a PSMA. PSMA is prostate specific membrane antigen. So we can make PSMA, fluoridated PSMA, like FDG. So, and PSMA is basically meant for scanning of prostate. And there is like other molecules like F-choline. It is also, but then there is a pharmacopoeia guideline for each molecule. You have to have different hot cell, because cross contamination is not allowed in pharmacopoeia, and this is injectable radiopharmaceutical medicines. So for each molecule we should have different hot cell, we should have different dispensing facility. So in terms of this thing, capacity building also, we were struggling. So we thought, let us develop it by our own. So that is how we started development into our plant. And as you can see here, we have developed different things like liquid target, ion source, transport container. Transport container, it is a lead shielded container for transportation of this thing, radioactive medicine. Like we develop hot cell and robotic dispenser. So this picture I am showing, it's a basically liquid target. of cyclotron. So this is a design for IBA cyclotron, and there are means 14 different parts fitted together, and that is how this liquid target is made. But then the target means reaction area where nuclear reaction happens, it is made up of niobium metal, and we call it as a target cone. So target cone is made up of niobium metal, and niobium is I would say it is neutral in terms of this thing proton reaction. So when proton beam is bombarded on niobium, it will not become radioactive, and that is why we have chosen niobium as a target cone material. And
so here I want to just, with your permission, pause
Yeah.
one.
Yeah.
So now it is important to understand that so many parameters that has to be considered before going to develop something. And the take home message is we focused on the critical success factors of developing anything, because otherwise this prototype will ultimately, for example, what he is saying, that you have to consider the pharmacopoeia, you have to consider a lot of other factors, and so this is the take home message actually I am considering.
Yeah.
From your talk, and please continue.
Yeah, basically, this thing material of construction is very important here, because and even composition. So and this is means prototype workshop. So I would like to give my input. What we did means we were having IBM target with us, and we got it scanned with this thing laser, and that is how we extracted the all the parameters like dimension and all. Now the next task was, what is MOC? Like the front portion here. Yeah, this front portion, it is made up of aluminum. So, but then one has to identify the grade of aluminum, otherwise it will fail. The this thing, this middle portion is SS316, and there is a separating ring between front and middle portion. So it is made up of PEEK, PEEK. It is a plastic, high temperature grade plastic, which can withstand up to 300 degrees centigrade temperature. And the back portion, this portion, it is made up of niobium. So we got it tested by weight chemical analysis, and as well as with SEM EDEX. So with the help of EDEX, we can find out that what is the composition of metal, niobium metal. And we found that it is a pure 99.99% pure niobium, and that is how we have chosen all the material, and then source the material and get it machined and fitted. And we tried and tested at our facility, and this liquid target we developed is working very satisfactorily. Now I will share the cost. The IBA this thing charges 70 lakh rupees for each target. So it basically in medical cyclotron there is a 8 numbers proton exit beam. So maximum we can fit this thing 8 proton this thing liquid targets there, and each target cost around 72 lakh rupees. So and we developed here in India, and it costed us the I think this is 11 targets we made, and it costed around 12 lakh rupees.
A big margin is there between cost and this price point, but there might be other factors for increasing this price, maybe not the raw material cost only.
Intellectual property.
Yes, intellectual property, transportation, logistics, and others.
Yeah. So and basically They have done research, lot of research. It is outcome of 30 more than 30 years of research. So basically, it cost us. So that is why they charge this kind of this thing money from us. So this liquid target, and then next, this is L bench. So in our plant, means if we want to perform maintenance of any target or iron source, so there is L bench required, and L bench is basically a lead shielded part, and we can stand behind that and perform the maintenance of this thing iron source or liquid targets. So in yeah, now this is something this thing hot cell and dispenser. So this portion is a hot cell, and this portion is it's a robotic dispenser. As I said earlier, it's a guarded area. All the sides means the door, everything, left side, right side, top side, everything is 100 thick lead shielding. So it's a basically like a cupboard, but then all the sides, walls, and everything are lead shielded, and to this thing prevent the radiation leakage. And this thing hot cell, it should meet the pharmacopoeia guideline, because there is a synthesis, and any leakage should be avoided. So we have to meet the guidelines, pharmacopoeia guideline. It's a negative pressure zone. So in hot cell area, there is a negative pressure, and then to avoid the radiation leakage, it's a 100 thick this thing lead wall. So there is a EERB guideline, Atomic Energy Regulatory Board guideline. So that one has to meet, and then only this reaction can be performed. So this hot cell and dispenser, it is made by Comeser, this company, Italy. So and this is already installed, and as a part of capacity building, we started, means we design our own hot cell, and this is our hot cell. So this is our proof of concept prototype hot cell we made, and we tested also, and this thing.
If you can, sir, if you can emphasize what is the difference and changes and iteration you have made, and on basis of from the proof of concept prototype to the final product.
Uh, Actually, we have got hardly chance to make more iteration, because uh, it it costs.
Think that it more improvisation and this has to be done in future.
Yeah. Uh, so the Yeah, in this earlier version, there was some finishing SS. So if you can look at this SS finishing. So feature-wise, it is same. We have tested, and at present we are in the installation phase of this. And feature-wise, in this hot cell, there is a one reaction chamber, and this chamber is for storage of waste. Our radio molecule is having 109 minute half life. So after 10-15 half life, we can throw the waste, and whatever waste is generated, basically when synthesis process is carried, there is a gaseous waste is generated, and there is a liquid waste also generated. So in this hot cell, they have created one reaction chamber and one waste chamber, and below this is for electronics and everything. So now in our case, uh, yeah, uh, we created a two chamber, upper and lower chamber, and we saw that the wastage generated airborne means radioactive wastage generated airborne and liquid, so it is in a small quantity, so it doesn't require a very large this thing chambers. So we shifted this thing waste chamber here, and that is how this is two hot cell in one this thing model. So that is the difference between this thing Commissar and our hot cell. And this is uh, this is our hot cell, and while we perform the testing of the hot cell, and these are all labels where radiation monitoring is carried by AERB. So
So at this point, I want to just convey a take-home message that the more clarity at the beginning of the day possibly one is having on the basis of the use case, on the basis of the all regulatories and
yes,
precision and all.
which is yeah,
So less number of iteration has to be made
yeah.
for developing the, and this will reduce the huge cost. So I want to pass to the students that message that be precise on the beginning of the day, not only depending on your technology.
Yeah, actually, while starting this project, it took around, let us say, 6 months for assembling this kind of the hot cell. But then we took 6 months for the documentation and all. We study feasibility. We study the feasibility, and we this thing understand. And we got unless we got convinced, we did not start it, because it cost means Commissar made hot cell. It cost around 3.5 crore, and this hot cell we built. It is also around 75 to 80 lakhs of rupees. So the initial for us initial phase was material, the right to selection of material, selection of the process, and we have given lot of this thing, and this thing, what is pharmacopoeia guideline behind this, what is AERB guideline behind this, and what the everything means parts and everything we have selected, and in most of the case means like foreign principle, they keep very close. I mean, the part fitted into the Commissar, like sensor and everything fitted into Commissar hot cell. If you go and ask the same company, like I want this part, so they will refuse. We have a memorandum understanding with this company, and we cannot provide this. So for us it was a challenge for us. So but then we try to find, and eventually we found the alternatives, and that is how we created. And this project looks very simple, but then it is as if means there are lots of interlocks, like if there is a reaction going on inside the chamber, so this chamber cannot be open, and because inside the chamber there is a 20-25 curie activity, and the human acceptance level is only 100 millicurie. And maybe curie is a new terminology for you people, but 1 curie is 3.7 into 10 raised to 10 disintegration of gamma rays. So it creates a lot of ionization. If one gets exposed, the red blood cell start reducing, and maybe if one gets overexposed, the skin hardness and brittle, the skin becomes very brittle, that kind of this thing health hazard can happen. So during the reaction, this hot cell will not open, and this hot cell basically the this thing PLC of hot cell communicates with the PLC of a cyclotron. So if you are performing the basically the liquid target of the cyclotrons are connected with the this thing synthesizer of this thing hot cell. So if door of the hot cell is open, the cyclotron will not load the target or will not unload the target, because if it unload the target, the directly 25 Curie activity, if door is open and the activity comes and accident can happen. So all kind of interlocks and safety measures are taken in designing of this. So there are lots of things involved, and that is. But then it was challenge for us. We took it and we finished it, and at present it is under the installation. Yeah. Yeah.
I was thinking that one potential thing that can be improved, maybe, I don't know, is that if one can see the reaction happening visibly. I mean, I am just
Yeah,
trying to.
yeah, you can
whether-
see there is a sighting window here.
Okay.
This is sighting window.
Okay.
And
right?
yes, it is a lead loaded glass.
Okay.
Normal glass, this glass and lead loaded glass can attenuate the this thing radiation, and normally the lead lead is basically poisonous, so we cannot keep it in a contact with a human. So a lead is enclosed into the SS this thing. But then attenuation of lead is very high, whereas glass has a less attenuation. So if you can see this window, sighting window area, it is 200 mm thick. So we have kept 200 mm thick. It's a 160 kg lead slab we kept, and it is transparent.
Transparent. Okay.
Yeah.
That was
So
I think if one can put a probe inside and see it in the computer so that we can visualize the reaction. Is it difficult to do?
yeah.
If we can put up some camera over there and we can see visualize from the screen that it may reduce the purpose of.
Yeah, we have tried, and many people have tried for that. But then this 20-25 Curie activity kills the camera sensor. So after, yeah, it's another kind of challenge. Yeah, yeah. In maybe in our cyclotron area also, means while the reaction is happening, means basically in oxygen nucleus, proton is captured. So and one neutron is knocked out. So during the reaction, there is a continuous neutron stream coming out from the cyclotron. So in our plant also we have tried to install many kind of camera, and even we try to shield it with the lead glass. But then lead glass is means lead glass can attenuate gamma radiation, but then it is transparent for neutron. Neutron can easily pass through and kill the camera sensor. So that is why we tried, but not possible. Or maybe if you can afford means 1 month life of the camera, then you can always go with that kind of solution.
So, because if use and throw model can be very simple, cost can, that is one solution. Or if the optic part can only be put into it and the sensor part is out, and then if it is also maybe possible. Anyway, we can continue.
Yeah, or maybe one can think about that. Means we can send the camera at the time of this thing. Means if you have any problem, or if you want to monitor the reaction and you send the camera, camera will go and capture the picture and will come back. So, and in our industry, means we are using a liquid target, but then for solid target, they use pneumatic shoot. So pneumatic shoot is basically like this thing, that hyperloop. So that hyperloop, a train travels into the tube like that. So in this thing, solid, the site where they are using solid target, what they do is they put this thing. Basically in solid target, they use gallium PSMA. So a radioactive substance is a gallium 67, and it is attached with the prostate specific membrane antigen, and then to create this thing, radioactive gallium, they put, means it is coated on the platinum tablet. So on platinum tablet they coat zinc, and then that zinc tablet is sent to the cyclotron, this thing, proton exit port, and then proton exit port, this thing bombard the this thing zinc and convert into the gallium. And then after that, after completion of reaction, that platinum tablet comes back into the this thing hot cell area, where it is immersed into hydrochloric acid. And platinum is inactive, means not reactive with the HCl, but then gallium is reactive. So it reacts with HCl, so all the gallium is dissolved into HCl, and then they mark with gallium mark with PSM, and that is how they create. So that kind of this thing, with this maybe idea, one can use pneumatic shoot and send the camera into it. Camera will capture and can take it back.
Endothermic reaction, for example.
Yeah.
So sometimes monitoring the heat is also the variables, the
Yeah.
temperature, for example,
Yeah.
reaction can be monitored using some probe. If it's
Yeah.
dipped in the reaction, that will give a more clear sense of what is going on actually.
Yeah, we have means in the synthesizer itself, there are provision. Means
Okay.
synthesizer can give information. First, the radioactive substance comes into a V vial. So near to V vial there is a detector. So it will show what we have sent from the cyclotron and what is received into the V vial.
Oh.
That is monitored. Then after the this thing, fluorine isotope is transferred into the reaction chamber, but then it has to pass through QMA cartridge. Now QMA cartridge is quaternary methyl ammonia. QMA, it can react with fluorine isotope. Means when fluorine and O18 mixture, H2O18 mixture pass through the QMA, the fluorine sticks to QMA and the rest of the things pass through it, and it is thrown into the waste. And then after eluent solution is sent into the QMA cartridge, so it takes away fluorine, radioactive fluorine, and take it to the reactor chamber. Now reactor, but then what do you think? What is the size of reactor in our case? Here we are talking about the picocurie. So while we load the H2O18, it is 2.6 ml. Yeah. So it's a like this thing 5 ml reactor. So I'm using the word reactor. Means it's not very big industrial reactor. It's a 5 ml reactor, and in 5 ml reactor there is the means I have seen many a times only 1 or 2 drops of this thing activity, but then it is 25 curie. So 25 into 3.7 into 10 raised to 10. And then that reacts, means we send monoglucose into that and acetonitrile and ethanol solution, and then it is 130 degree. But then you are talking about this thing temperature. Temperature is continuously and graph comes out. So temperature, pressure, the activity, everything we can monitor in real time into our synthesizer, like that. So, and then it is transferred into dispenser, and then dispenser, we fill it with vial. This thing FDG is filled with vial. So the receiving quantity from cyclotron is 2.6 ml, and then the final reaction happens, and the synthesizer itself adds some this thing deionized water into this and dilute it, because in 2.5 there is a zero point 0.1 ml is a activity, and 0.1 ml I have to distribute between 25 hospitals. So the this thing, yeah, dilute it, and means it dilutes into 20 ml. So initially it is 20 curie, but then, and this thing, the activity is continuous, means during the synthesis process also it is decaying, during the dispense process also it is decaying. So the synthesizer dilute it to 20, means add 20 ml, and then we get around 21 ml at the this thing bulk vial into dispenser, and from dispenser we dispense, like in human body for carrying the PET this thing diagnostic, it requires around 10 millicurie of activity. So if the hospital has 10 patients, then they will order 100 millicurie. But then we cannot dispense 100 millicurie and send it to them, because we have to look into the half-life. Suppose, for example, if I want to send the activity at Kokilaben Hospital, Indore, then I have to consider 3 half-life. So this thing, if they order 100, then I have to fill this thing 800 from here. So 800 to 400 in 109 minutes, 400 to 200 in again 109 minutes, and then again in 109 minutes it becomes 100 millicurie. That is how. So at the time of loading means we generate 20 curie, but at the time of injection we deliver 2 curie. So 90% of our activity is decayed. So that is how we this thing operate this thing MSA Gujarat, and in our MSA Gujarat we have created such this thing machines and technology. Now, next is my journey to this thing technology development. And in the beginning, as I said, I was in this nuclear spectroscopy group, but then I was in MS University Baroda, and with this thing hyperfine interaction group. But in that group, means we were doing some work on semiconductor. So there I started developing things. Normally, during the research career, or maybe when you are PhD student, one hardly thinks about creating things. But then, basically, it was, I can say, we were not having any facility for doing research in nuclear physics. So anything means even the material we order, means we were doing work on this thing semiconductor, and work in semiconductor requires chip grade material. Now chip grade material is having 5 N purity, and we hardly get such kind of material here. And means in university, if one send the this thing purchase requisition, so there are other 10 research scholars standing saying that I want this and I want that. So even we were not getting this thing materials, or we were not able to get the any kind of this thing equipments and everything. So I started creating my own equipments during my research. So this thing hyperfine injection, and during my research also I made superconductors, and these superconductors I did not make for my research work, but then there was a science fair into the Jainit school, and Jain school approached us saying that we wanted to demonstrate the magnetic levitation. So how magnetic levitation train uh, work, and so that is how they approached us, and they said, give us some this thing working model for demonstration of this demonstration at a science fair. So I created a superconductor, and it is YBA2CU307 based superconductor, and that I given to Jain school for the demonstration. And the next is material purification. Now, I would like to discuss this topic of material purification. Now, means literally struggling with this material impurity and all. So I met one chemistry person. So he said, in chemistry we don't get HPLC. To carry out research in chemistry, we require all the reactants HPLC grade, but we hardly get. But then we purify it. We pass it through multiple distillation, and maybe if we require anhydrous reactant, then we pass it through silica gel, and that is how we purify our material and then do research. So maybe in your case also, he said, I don't know, but then in your case also you can think about it. So then I started searching how I can purify my material, and then I found that for this thing getting semiconductor chip grade material, so there is a process called zone refining. Now, this is a very different term. Maybe person from metallurgy or physics can understand this, but then I will explain it in a very short. So, zone refining is basically if one take the ingot, maybe a solid of the material, and there is a arrangement of ring-shaped furnace. So that furnace can create temperature near to the melting point. It's a 20-degree below to melting point of the material. And then from the long ingot of the material, the ring-shaped this thing furnace pass slowly, maybe 1 micron in a 1 minute. So that is the passing rate. So if we give multiple pass of zone refining, so then material gets purified, and the impurity is sent at the end of the material, and that is why that is how I created cheap grade material and carried my research. And after that, I was doing Mosbar spectroscopy. So
Atom is happening
yeah,
only, and there's displaced.
yeah.
Semi-liquid state. Sort of.
We actually we were keeping, and it is documented also. We were keeping.
When you cut that.
Yes, it is cleavage crystal. This thing cutting of the crystal from the cleavage plane. But then we keep temperature 20 degree below the melting point. So at that temperature, the atoms becomes mobilized, and in solid state material, it is always tendency that the like metal is this thing placed. All the like metals, atoms are placed adjacent to each other, and the unlike, yes. So all the like atoms are placed near to each other, and unlike atoms are this thing forced to go away, and that is how it goes away at the both end of the this thing crystal, and then after we cut the crystal, and that is how we were getting 99.99 pure this thing germanium and antimony. My research material was germanium and antimony. And then after in Mosbar spectroscopy is carried out from maybe liquid nitrogen temperature to 500 degrees centigrade. Now from liquid nitrogen to room temperature we were having facility. We were having closed cycle refrigerator in our laboratory, and we were creating this thing. But then our interest was to understand and carried out the work at higher temperature, and it was in the field of magnetic semiconductor. So, and then there is a dire need of creating a furnace, and there was this thing dimension limitation in Mosbar spectroscopy. There the distance between source and detector is 100, and source is oscillating, and it has displacement of at least 10 millimeter. So there was a requirement. I have to create this thing maybe 5 centimeter, 50 mm thick, and 100 mm in diameter furnace, which can go up to 500 to 600 degrees centigrade. And then this Mosbar is very sensitive to iron. So in creating the furnace, I cannot use a single piece of iron. Otherwise, it will pick up signal from the iron and will give it into the spectrum. So that setup I created by my own in MS University. So, so this is typical setup. But then in second half, I will maybe, if you are interested in knowing how I design the this thing furnace, high temperature furnace with the dimension of 100 mm diameter and 5 centimeter thickness. So that I will design. I kept it this thing. I thought I will design in front of you people, and that is how you will get the idea how to design or maybe create any device or so. So. And then after I joined ERDA, means after completing my PhD, I joined ERDA, and in ERDA I was instrumentation expert for scanning electron microscope, EDEX, XRD, and sputtering and this thing. Maybe we were performing gold sputtering and platinum sputtering for characterization of metallurgical samples. So I was instrumentation expert there, and in ERDA we were having some extra duties. Means our director came and said that you people are sitting with this advanced instrumentation, and already your PhD is into your field. Why don't you this thing involved into development of some technology like that? So that is how I involved into development of this thing, hydrogen storage material. Basically, hydrogen storage material is material used for this thing hydrogen storage and this thing hydrogen based vehicle. So that material we were developing in ERDA, and in this thing maybe in ERDA I have designed large capacity ball mill. Basically, for making hydrogen storage alloy, it requires a ball milling machine. So ball milling is a machine for creating nanoparticles. It's a top-down approach, and it's machine for creating nanoparticles. But then the this thing we were having imported ball milling machine, and its capacity was around 100 ml. So at the it was creating a very small amount of material for research purpose. But then we wanted to commercialize, and we wanted to demonstrate the technology outside. So for that, I made this thing ball milling machine by my own. So this technology I developed there, and here also in ERDA also we were facing some challenge. We were creating hydrogen storage alloy for this thing storage of hydrogen, and it's a magnesium based material, magnesium nickel based material, and in the lattice structure of magnesium is such that the it is cubic in nature. Lattice is cubic in nature, and at the 8 corners of a cube there are magnesium, but the void into the magnesium material is exactly of the size of hydrogen. So if one allows hydrogen at higher temperature, means at higher temperature the molecules become mobilized and vibrates. So they displace from their position and the void becomes large. So and that is how hydrogen gets penetrated into the magnesium matrix and then stays there. So at high temperature, it's this thing stored, and then if you want to retrieve hydrogen from the material, then give further still higher temperature. So then it can be retrieved. So it is a technique for safe handling of the hydrogen. Hydrogen is explosive material, but then if you store it into the magnesium matrix, then it becomes a solid this thing storage, and then it is not harmful or maybe not explosive. It requires some temperature to this thing dissociate from the magnesium, and then one can use it. So it is a safe handling technique.
Converted to magnesium and vice versa.
Yeah. Lithium has a very strong bonding with the hydrogen. So if one reacts, then it becomes a stable bond. It will never dissociate. And we have tried with the sodium hydride, we have tried with the aluminum hydride also. But then alu- uh, aluminum lithium hydride works. It stores the hydrogen at around 2 to 20 degree and release the hydrogen at 250. But then in our case, in magnesium based material, we were getting enough storage, means at 90 degrees centigrade and 130 degree, and for the commercial application of anything, it involves, means if lithium based material involves 230 degree or 250 degree, and this material can operate at 130, then always people will choose the lower temperature, because uh, one has to give energy to this thing release the this hydrogen. So that is why we were working on magnesium. So here there was a challenge of purification of hydrogen. We were getting hydrogen from this thing outside, and we performed GC, gas chromatography, but then we saw that there are lots of impurities in hydrogen. So for hydrogen storage alloy testing and everything, we were having challenge. So I made this thing setup for purification of hydrogen. So yeah. So this is the typical arrangement of hydrogen storage setup, and there is a reservoir. So we fill the reservoir with hydrogen at 50 bar, and then this is a reactor. Yeah. So this is a reactor, and in the reactor we used to place the this thing nanomaterials for hydrogen storage. So then it react, and we allow by opening this valve, and this valve, hydrogen is allowed to come into contact with this material, and this oven gives the temperature to the reactor, and that is how it's stored. But then we found that after maybe 10 or 15 charging, the material becomes inactive here. So then it will never further charge the hydrogen. So, and we wanted to purify the hydrogen. So we introduced this thing, purification reactor. And what we were doing was, in purification reactor, we used to keep sodium metal and open the valve here, and leave it overnight. So in maybe in 12 or 24 hour, all the oxygen and whatever impurity that is present, reactive impurity basically, so that will react with sodium, and then we used to close this valve and then allow to react, and that is how we enhance the life of our this thing hydrogen storage material. And we have filed patent, and this patent is granted. So now, after working at ERDA, I joined a company called Star Laser. So Star Laser is a company involved into manufacturing of all kind of lasers. So we were making 3 watt laser, 5 watt laser, and this uh, intense pulse light. Now this intense pulse light, it is used for unwanted hair removal. It's a beauty product. So maybe you will find New Look Laser Center in Baroda and many cities in India. So the all the machine means in New Look centers, they this thing the skin doctors, maybe dermatologists are running those New Look clinics, and in our New Look clinic, uh, I made intense pulse light this thing source. So intense pulse light, it gives uh, pulse of intense light, and it kills the hair follicle. That is how unwanted hair is removed. So that device I made, and then neodymium YAG laser. And neodymium YAG laser has the property, it is having a bleaching property. So if we focus neodymium YAG laser on some tattoo, on people make tattoo and then go for opt for the this thing military employment, or maybe air hostess kind of employment, then they reject just because candidate is having tattoo on their hand or maybe anywhere. So uh, tattoo can be removed with the help of neodymium YAG laser. Normally, if one wants to this thing remove the tattoo, then it requires plastic surgery. But then with the help of neodymium YAG laser, one can remove the this thing tattoo. So that tattoo removal we were making. Then design of 3 watt dental bleaching. Now, this dental bleaching is used for this thing, decoloration. Means people eat a lot of gutkhah and supari and everything, and this thing, the teeth are damaged and maybe colored. So, to bleach the teeth, there is a device called LLLT 3 watt laser. So with the help of 3 watt laser, one can remove the this thing stains and everything from the teeth. So that device I was making. Then hydroderma abrasion. Now this normally in beauty parlor, this is a product for beauty parlor. So hydroderma abrasion, normally for this thing bleaching, they use some chemical. So chemical bleaching is suited most of the people. It is suited for most of the people, but in some case, uh, some reaction happens, and maybe people get some allergy or maybe rashes and everything. So hydroderma is a alternative of chemical bleaching. So and there is for bleaching, some beautician use corundum. Corundum is a sand. So they throw this thing, higher energetic stream of corundum on the skin, and then it takes away this thing, one layer of skin, and that is how they perform bleaching, facial bleaching. So in our case, we were not using any chemical, or maybe not the sand, only water jet. High this thing, high energetic water jet can take away the skin, dead skin, and that is how this thing bleaching is performed. So that device we were making. And then this cryolipolysis. Now this cryolipolysis is basically a device for fat removal. Now it is clinically proven that this thing, if one means like a belly fat or maybe this visceral fat, so if one gives this thing temperature shock, mean suddenly take it to -8 degree and suddenly take it to 42 degree. So that kind of shock, if one gives to the adiabatic fat, then fat structure breaks, and then in our body liver metabolize the unwanted fat, and that is how this thing fat can be removed. So maybe beauty conscious people used to come at our clinic, and then we were performing fat cryolipolysis, fat removal. So in cryolipolysis, we made a device which can take the temperature, which can give temperature shock basically. It can take temperature -8 degree suddenly, and then take at higher temperature 42 degrees suddenly, and that kind of temperature shock we were giving, and that is how the cryolipolysis removes the unwanted fat. And then uh, 810 nanometer dicrocystorhinostomy. Maybe you may be this thing familiar with the term. Dicrocystorhinostomy means there, many people, it means there is a arrangement of some kind of channel from our eyes to this thing throat area. So all the tears and all the this thing, maybe any unwanted particle or anything comes into our eye, it is this thing passed to our throat area, and that is how it is removed. But then some people get it blocked. The channel, this thing, the channel from eyes to throat blocked, and there is a continuous tears coming from eyes. So in dicrocystorhinostomy, we used to pierce the flexible cannula. So we were having flexible cannula that we used to pierce into the ear channel, and then this thing cannula stops at the place where this thing channel is blocked. So then after we used to fire in cannula, there is a laser arrangement. So we used to fire that. So laser burns the this thing obstacle, and that is how we pass the this thing whole cannula from eye to throat. So and when we put endoscope into the patient's mouth, we can literally see that laser is coming from the throat area, and that is how we ensure that channel is cleared. And then after, at the end of cannula, there is some mechanical notch kind of arrangement. So we put some thread, this thing, cotton thread there, and take away the cannula. So thread and pass from this thing throat to eye, and then this thing, we use some enzyme ointment and antibiotics to heal. So after maybe 1 week or so, that this thing channel gets healed, and then take away the thread from the eye. That is how dicrocystorhinostomy is performed. So for application in dicrocystorhinostomy, we were making this thing 810 nanometer laser. Now 810 nanometer and 150-watt laser for urology. Basically for urology, people use holmium laser, and it has a wavelength of 1520 nanometer. But then we have tried, uh, even with the help of 810 nanometer also, this thing, kidney stone can be removed or maybe destroyed. So this thing, the holmium laser involves this thing, flash lamp pumping and heavy electronics and water cooling and all. But then for solid state laser, we were making very small kind of benchtop model, and with the help of that, we were able to perform this thing, kidney stone operation. So that device I was making. And then for varicose vein also, this 810 nanometer laser I was making for treatment of varicose vein. Now, varicose vein means some people with profession means while working they are always standing. So in that case, they get some veins coming out from the skin. So and it becomes painful when basically it's an uncontrolled growth of a vein, and vein becomes this thing large in diameter, and it comes out from the skin, and it becomes painful. So for healing this thing varicose vein, we were making a device, and the procedure was very this thing normal. One has to pierce the cannula into the vein, and then fire the this thing cannula goes up to the end of the this thing this thing vein, swallowed vein, and then fire the laser, so it will shrink the vein, then again take away cannula, fire the laser, it will again shrink, and that is how take away you can take away cannula, and means without any surgical any kind of procedure, but just by creating one this thing hole, one can eliminate varicose vein. And there are lots of machines installed in Baroda, and it is made by our company. I was involved into making of such machine. So this all machines we created at this star laser. But then here I wanted to bring this thing, one thing into your notice. Now we were making very good machine, but then at the time when we were involved into this business, we were having some poor sense of aesthetics. Our machines, our machines were rugged. It was very good in performance, and there was no complaint at all from the doctor side that your machine is malfunctioning, or maybe it is not working, or they are unsatisfied with the performance with our machine. But then all the doctors were not happy with the look of our machine. They used to say we are expecting a kind of a luxury car, but then you are always coming with trucks. Like those kind of comments were coming from the doctors, and I mean we were taking the whatever that is available into the market, that we were giving. We go to GIDC and see that someone is making some enclosures or maybe panel. So we give them order and say, we will this thing customize that enclosure for our purpose and take away, and then fit all the thing laser and everything into machine, and with the this thing attach PLC and HMI, and give it to doctor. So some doctors were happy, they have no complaint, but then especially the beautician, they said, "Ki bhai, here the clients are beauty conscious," and when they look at your machine, they goes away that this is poor machine, and we will not go for any kind of beauty treatment with this machine. So I will show you my machine, and maybe I will show you Quanta machine also. Quanta is this thing Italian company, and there was one company called BioLitech. So Quanta and BioLitech, they were making machine, beauty product machine, and we were into competition with them. And then eventually we realized that the aesthetic look of the product is important. So and that is how we improved our product. So I'll show you this thing. Yes. Yeah, this is a Quanta made machine. This is a machine for this thing, unwanted hair removal, maybe it is all in one. Unwanted hair removal, tattoo removal, and wrinkle removal, everything one can perform. and this machine comes with the this thing leukoderma. So basically, as we all know, leukoderma cannot be cured. But then the company was supplying some kind of dye. That dye we have to inject into the patient skin and then expose it with the laser. So with the while we expose it with the laser, so that dye gets darkened, and that is how we were matching, and we have to give exposure till the tone matches, and that is how this thing we were performing means leukoderma, and it can means it can stay for at least 6 months and then goes away. Then again one has to come and then perform the this thing tone matching. Yeah. 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 I'm not aware because means this thing we could create all this kind of laser we could create. Uh, yeah. Yeah. No, 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 no. We and and anything actually we were making this laser, but then anything you pierce means inject it to human body, the regulations are very this thing I can say tough regulations are there. So for skin treatment and all tone matching, any skin treatment, tattoo. Yeah. Yeah, regulation come, but then we were successful at such for this varicose vein. We introducing cannula into this thing vein, or maybe for dichrosis to rhinostomy also we used to introduce cannula, and then we were performing operation. So in that case regulations were applicable. So to this thing avoid the conflict and everything, what we were doing was we were making, then the part which was coming into contact of human body, that we were using from BioLitech. So we used to make this thing laser, but human contact parts BioLitech or Quanta that we were using. So yeah. So this is the machine I made. It's called intense pulse light source. Our earlier machine, our our earlier machine was this thing like a just like a rectangular box. But then later on we improvised and we made the. So this is our intense pulse light machine, and it is used for this thing unwanted hair removal, or maybe wrinkle removal, scar removals, and treatment of leukoderma. And this is the I was manufacturing for this thing neodymium YAG and 10 nanometer kidney stone removal. Maybe my voice is, I think, large enough. I don't think nobody can hear, or maybe so. We will go without it. No problem. So this machine I was making for this neodymium YAG and 810 nanometer kidney stone removal. So I want to discuss one case which has come at the Ford company. Now, the kind of the mindset customer has. One customer came to Ford office saying that means there was an ice cream parlor and maybe you must have seen there is a drive-through this thing restaurant, McDonald's restaurant in Sama. So same thing was there in US. So there was an ice cream parlor and there was a drive-through arrangement. So customer goes into this thing ice cream parlor by driving a car and then takes ice cream and drives away. So customer came saying that when I buy vanilla ice cream from the ice cream parlor and comes back and start the car immediately starts. But then when I this thing buy American dry fruit and comes back, car doesn't start. So this is the problem in your car. So, but then it was complained and very seriously taken at the Ford this thing manufacturing facility in US, and then Ford company deputed two engineers to have a look at the situation, and then engineer came with the this thing person. They entered into drive this thing through passage and stopped the car, take the vanilla ice cream, came back and start the car. It immediately starts. And then second day they came, again they bought the American dry fruit, and then it doesn't start. So even Ford engineer noticed that when they buy American dry fruit, the car doesn't start. But then it was nothing to do with the flavor of ice cream. It was basically time. Vanilla is the base. So when he goes to the this thing ice cream parlor and take the vanilla, the time taken was small. And when he take this thing American dry fruit, he has to mix everything and then give and the time taken was this thing higher. So that is how they found, and finally they this thing investigated into the injector, and they found that the earlier diesel car engines were very poor. You have to start the heater first, and then it takes 2-3 minutes or maybe 5 minutes to heat the chamber and then start and everything. So those kind of problem were there into the diesel engine, and there were some problem into injector also and fuel tube also. So they improvised, and then finally the problem was resolved. So means whenever all you people are coming with the mindset of maybe startup or creating prototype, so always uh, try to welcome any silly ideas of the customer cannot be wrong. Always take this policy and go ahead. Even in our case also, we means customer were complaining about the aesthetic look of the this thing machine, and we improvise, and we have installation maybe around 250 installation in India, pan India. We were operating in India maybe all the new look clinics. The machines are built by us. So like that. Now, yes. So in our company, our director used to say, if among the all cabinet, computer cabinet, iMac is catching the eye, because if you look at it, if you see the build quality, it is unibody construction and everything, aluminum, this thing finish and everything. So even in mobile also, Apple phone catches the this thing attention always. It is there. So and creating the such kind of device, maybe Apple they have not used means any fancy shape or anything. They use very basic shape, and though their products are catching this thing attention. So our director sir said, I want to create laser like this. So maybe in the second half, I will show you how we created such a device in our factory, and will give you idea of how to create this thing AutoCAD, this thing design of this machine. Now, yes, work at Savli Incubator. Basically, I joined Savli Bio Incubator in 2000, maybe 2012 end, and I was here for 1.5 years. But most of my work was related to administration. I could not develop this thing, or maybe I was not involved into any technology development task. And it was those days where means if you enter into this incubator and near to that stairs, there is a map of incubator. That is created in my computer. I created it. Even maybe every partition and everything I created, maybe a lab or any electrical plug you see here. So that is designed into my computer. But then it was not anything to do with design or maybe prototyping of any device. Mostly it was administrative and this thing CAD design work I did here. But then while sitting here, I came across this thing, many this thing aspirant and maybe incubatee, and got the personal projects here. So I'll show you my personal project. So I did this thing, ball milling machine I made during my ERDA work, and the same ball milling machine. Basically, this ball milling machine I made for Sigma Energy Technology, and there is a arrangement of four this thing bowl here, and there is a sun wheel. So this motor mechanism rotates the sun wheel, and in ball milling machine the bowl is rotated in opposite to sun wheel rotation, and that is how maximum shear force is transferred to the material, and that is how nanomaterial is created. So this ball milling machine I made for Sigma Energy Technology, and then yeah, and now Sigma Energy Technology was this thing Baroda based entrepreneur, and they were into manufacturing of indium tin oxide, this thing sputtering target. Now indium tin oxide, indium tin, it is used for making this thing solar panel. So in solar panel there is a transparent conducting layer coating on the glass, and after that there is a N layer, there is a P layer, and there is a copper buffer layer. So this company Sigma Energy was making indium tin oxide sputtering target. Now they wanted to test it. Now for testing they required sputtering machine. Now this thing sputtering machine from the professional manufacturer, it costs around 6 lakh rupees. Now this company approached me, and I created sputtering machine for them, and maybe I made it for free of cost. But then in sputtering machine there is a this thing 3000 volt this thing potential difference between sputtering target and substrate, and there is a vacuum arrangement. So in this fine vacuum 10⁻³ vacuum, and then high voltage is applied between target and this thing substrate, and the substrate is coated with this thing target material. So this is the procedure. So I created this sputtering machine with the help of I took this thing transformer from microwave. So microwave transformer has a voltage around 2000 volt, and then if one rectifies it, it becomes around 2800. So that is how I could create 2800 to 3000 volt and then apply. But then this is low cost development. The this thing entrepreneur was having this thing a very low budget for testing of their product, and for them I made this sputtering machine. Yes, now plasma spray coating. Now the same company, the Sigma Energy Technology, I made ball mill for them, or maybe sputtering machine for them. The same company, they were making ink for printing on the mosaic tiles. So it is inorganic this thing oxide based material which has some color, and I think there is a color combination called CMYK, cyan, magenta, yellow, and kind. Yes. So four color with the help of four color this thing combination, they can create images and everything kind of printing on mosaic tile. So that color they were making, and actually they were into manufacturing of ink, and they wanted to test their ink. But then what happens? If they wanted to test the ink, then they have to give ink to this thing tile manufacturing company. Now tile manufacturing company, they they were not ready to take their ink because their ink were not certified or not tested, and they were not sure. They say कि भाई if we print our tile with your ink, and if batch fails, then we have to throw away all this thing calcified tiles, and we cannot take and your ink, because there is a SACME. There is one company called SACME. So they manufacture printer for printing on tile. So this thing, if your ink goes and choke into SACME machine, then we cannot take the risk of this thing spoiling our SACME machine. So nobody was ready to take their material, and they wanted to test it and prove. So they came saying that means, and it is difficult. It was a very small company. So they said it is difficult for us to arrange a kiln furnace. Tile manufacturer, they have kiln furnace. So same kind of furnace we cannot afford into this thing, and we are thinking of using some maybe high temperature process. If we can this thing sinter the ink with the help of flame also. So we tried with the flame, but then all the means oxybutane flame or oxyacetylene flame, there is a lot of carbon into flame itself, and there is a water involved. So that water and carbon was spoiling this thing ink seed. So then they came saying that we want some clean process in which we can create high temperature, but then there is no carbon or maybe no water is there. So then I started making this thing plasma sintering machine, and this is the typical photograph of this thing plasma created by this thing our plasma gun, and I think this is whole machine. So this machine was installed into Sigma Energy. It is specially designed for sintering of ink for tiles industry. Now, yeah. So next is this thing diamond imaging. There is one company called Sarin. It is Israel-based company, and they make model Galaxy 1000. Now this Galaxy 1000 model is a machine meant for uh, evaluation of a raw stone. Basically, this is diamond imaging machine, and a raw stone coming from any mine. So they put it into this machine, and with the imaging of they can create this kind of image, and this machine, the program in this machine predicts what is the maximum size of diamond that can be cut from this stone, and from where to cut. Everything, every information it gives. And basically diamond is a material having highest refractive index. Its refractive index is 2.4, and when we try to illuminate diamond from outside, the light doesn't enter into the diamond. It completely reflects, and the inside of the material cannot be illuminated. So in this machine, we were creating this thing refractive index higher than the diamond outside, in surrounding of this. And there is no secret, as such there is no secret. Liquid selenium, selenium is a metal in periodic table, so liquid selenium has a refractive index of 2.44. So when we immerse this thing diamond into liquid selenium and illuminate it with the infrared radiation, so the inside of the this thing stone can be means you can visualize optically, and you can literally see. Diamond is created into the coal mines, and there is a chance some sand particle is inside the material, or maybe there is a micro cracks, or maybe any kind of impurity enters into the diamond. So that can be avoided if one gets the image of diamond from inside. So for quality and evaluation of a diamond, Galaxy 1000 from Sarin, this machine. Now there is a Surat-based company who was interested in creating this machine in India. So I took this project, and yeah, so this machine I have created, and we change the aesthetics basically, because we cannot take the same shape, otherwise they will infringement, maybe patent infringement, or maybe violation. So that kind of case they can launch onto us. So that is why we created this machine, and this machine has the same functionality as a Galaxy 1000 Sarin machine. And this image of a raw stone was taken by our machine. And for making this machine, means we reverse engineer the whole Sarin machine, optics and everything. I went to China, and then there is a company called Crystech. So I gave them optics and every part to reverse engineer. But then within 3 days, they could create everything, optics and non-refractive coating, everything, and then gave it to us. And then we started assembling here this machine, and we started manufacturing. So now, yeah, this thing. Now in this machine, one can create the image of diamond stone, and there is a software. It can predict the maximum size of diamond that can be cut. But for cutting of diamond, DPSS means diode pump solid state laser is required. So for diamond cutting industry, there is one company called Northrop Grumman. Is an Israel-based company, and they were having monopoly. They were making diode pump solid state laser. So we intend to reverse engineer, maybe copy the same Northrop Grumman kind of laser. So then we started working on it, and yeah, so this thing, laser diode pump solid state laser we created at Baroda, our factory, and we tried, and it is as efficient as Northrop Grumman. Yeah. So yeah, and then after this microwave friendly tray. Now, in maybe in foreign country, there is a huge market for microwave, because they take the fruit from the maybe mall or this thing, and microwave and eat it. So I got the assignment from some New Zealand company that they want some microwave friendly tray. So I started making this thing. Initially, I have to send them 100-piece microwave friendly tray, and they gave us sample. They came saying that you replicate this and give it to us. If it pass through test, then we will buy from you. So this is a benchtop molding thermoforming machine we created, and with the help of this thermoforming machine we manufactured this tray, and it was through into trial and everything, but somehow the this thing order could not materialize, but then we created this thermoforming machine for benchtop verification. And I earlier shown you this Quanta made machine. This is for this thing, dermatological application. But then Quanta stopped this machine, and after that they provided support up to 10 years. And after 10 years, there were no support for anything, means optics part, laser part, power supply part, PLC part. So, and there were many installation in India, Quanta and BioLitec, and all the doctors were in need. So they said, why you are coming with this laser and intense pulse light source, but if you can repair this machine, then only I will give you order. So that kind of condition doctor used to put forward. So then I started working on the this thing hardware, and I replicate most of the board of this thing Quanta. So basically it's a PCB designing task. So I did it, and I had designed all the PCBs of Quanta and replicate, and it was working satisfactorily. Yeah, now this is design of XRF. I took this project, XRF project, from one of the this thing jeweler. In jewelry market, they use XRF, and this XRF is used for this evaluation of gold or maybe silver and percentage of gold, and there is a flux mixing, tin mixing or silver or copper mixing. So evaluate that. They use the machine, and we replicate this machine successfully, and it is installed at the this thing. And yes, I took this project, and while I was working in STBI, I took this project from this thing Kutch based, Anjar based this thing industrialist, and they were interested in making biodiesel. So, and biodiesel from used cooking oil. So they were interested in making it, and I can give the idea, means for making biodiesel, one has to take used cooking oil. And then the step is like that. Use cooking oil, then treat it with the sulfuric acid overnight, and then neutralize. And then after this thing acid neutralization, if we put this thing use cooking oil and sodium methoxide as a catalyst and a methanol, and heating and stirring. So used cooking oil gets converted into methyl ethyl or maybe methyl ester and glycerin. You are from the bio background, so you will understand. So that project I have taken, and biodiesel can be made with two different this thing routes. One is a harsh chemical route, means sulfuric acid or sodium methoxide or kind of, and the second route is bioenzyme. Yeah, there is a means even fat can be digested into human body, and the digestion of a fat is through lipase. So there is one fungus called Candida antarctica. So Candida antarctica make this thing lipase, and that lipase, if we treat this thing, use cooking oil with Candida antarctica, then Candida this thing this thing lipase can convert use cooking oil into this thing biodiesel and glycerin. But then diesel made from harsh chemical route and diesel made from this thing or this thing green chemistry route, both are different, because the green chemistry route, in green chemistry the glycerin is pharmaceutical grade glycerin. There is no contaminant, and soap industry can direct buy it. Whereas if we make it through harsh chemical route, then we have to purify the glycerin. Otherwise, they cannot use. So I made it through both the routes, and means we created small benchtop verification into this thing our factory, and we perform this esterification reaction, and this thing separated. Here you can see the diesel separated from used cooking oil, and then after we intended to scale it up. So this is a typical schematic of process machinery required for this scale up the this thing diesel manufacturing. And then we discuss this thing schematic with GMM Fodler. Maybe GMM Fodler, you know. GMM Fodler is a process industry. So we discuss this schematic with GMM Fodler. We discuss it with Linde also. But then both the companies were ready to make process machinery for us. But then their charges were above 4 CR. So it can literally kill the idea. So then eventually what we did, we went to Alang shipbreaking yard, and from this thing we were requiring means 6-7 tanks. So that tanks we bought from the scrap in Alang shipbreaking, and then took it to Baroda and then modified, and we created our own biodiesel manufacturing plant. So this biodiesel manufacturing plant we created by modifying the tanks purchased from the scrap from the Alang shipwrecking. And you will surprised to know it costed around 9 lakh rupees to us. So, and this is typically a work I did for this thing ISRO. In ISRO laboratory, they were making some micro antenna, and the size of antenna was around 500 to 1200 micron, means 0.5 to 1.2 mm. That small size of this thing antenna they were making, and it was meant for sending into the space. But then there is a practice in ISRO. They test it first. So they create this space kind of environment here in laboratory and test the performance of their this thing antenna. And basically this is cheap, but then these all are contact made for testing of a chip. So they were keeping many of such antenna into the vacuum chamber, and while they were starting evacuation, the chip goes away into the this thing vacuum line. So they came saying that we want this thing, some kind of catcher kind of arrangement. You make it for us, and then we wanted to test this thing micro antenna. So I built first prototype for them, and it was the material of construction was mild steel. So they tested it. They said, okay, your this thing catcher can hold the micro antenna, but then if we want it the 100% gold, pure gold. So then, yeah. So then I created this thing 100. I created micro the antenna catcher from 100% pure gold with the help of some jeweler into Baroda, and given it to this thing ISRO. So this project I did with ISRO. Yeah, I'm finishing. 5 minutes. Now this atomic magnetometer. Now maybe this term is new for you people, but then atomic magnetometer is a device used for mapping the brain signal. Basically, it is a very sensitive this thing magnetic sensor, and normally for mapping brain they use a squid. Squid means superconducting quantum interference BI. But then squid operates at liquid helium temperature. So means it can squid cannot be handheld. Always one has to take the patient at the hospital like MRI or CT scan. So kind of machine. So in that patient has to sit, and with the help of squid they analyze the brain signal, and it is used for early detection of Alzheimer, early detection of this thing, possibility of a brain stroke. So there is a one other incubator iCreate. So in iCreate incubator there was incubatee Shilpa Malik and her group. So they were interested in building this atomic magnetometer, and they were intended to make the device for brain mapping. So I was helping them making the atomic magnetometer. So the requirement was they want the oven of the size of maybe 50 millimeter by 20 millimeter size of oven, in which they can rise the temperature from 35 degree to 500 degree, and in a very controlled manner. So they wanted such kind of oven, and in atomic magnetometry they use some alkali metal rubidium cell, and rubidium cell is pumped through a laser, and with the help of laser they can sense the magnetic signal coming from the brain. And I created all the hardware accessories for this thing Shilpa Malik group, and this is schematic diagram of atomic magnetometer, and this is the device I created for them. So there is a laser mount, there is a optics mount, there is a oven 50 millimeter in dia, and this thing and there is a this thing pre-optics, post-optics and detector. So this arrangement I made, and this is the individual part of the atomic magnetometer. So this thing iCreate and Shilpa Malik group were in collaboration with one Israeli scientist called Harry Euclid. So Harry Euclid was helping them to create atomic magnetometer, and it is this magnetometer was very successful idea, and it can measure magnetic field of the order of 10 raised to minus 15 Tesla. So that kind of sensitivity it was having, and even we have checked it. It can sense the signal of heart. In heart there is a blood continuous blood circulation. So and blood in due to this circulation and change in current, there is a magnetic field associated with heart. And if you put this atomic magnetometer near to heart, it was sensing signal from heart. So this device we made, and then this development of fetal scanner. This device is used for
Heart has, this blood has iron in it. So it will be able to sense the iron. It is iron phosphorus complex.
but then that iron, the protein attached with the iron, this thing hinders the magnetic field of iron. So this it is a very sensitive magnetometer, but then though it cannot sense the iron, it basically senses change in electric field. And wherever there is a change in electric field, there is a magnetic field associated. So that magnetic field can be sensed. So that is how it was working. So and this fetal Doppler, so it is used for this thing monitoring the heartbeat of baby. This thing if into pregnant ladies, the monitoring of heartbeat of a baby. This device is used, and this thing fetal scanner. Whenever there is a image created, so there are a lot of restrictions. But then if one don't create the image, then this device can be easily made, and this thing can be sell into the market. So this device I created while sitting in this thing, this STVI, in 2012. Yeah. So that's all. So maybe we can take a lunch break, and then after the lunch we can continue with some design idea, or maybe we can discuss the this thing.
Yes, that will be better. After the lunch break, we can possibly go through your experience, and we have learned your experience, but your message to how to develop the prototype, how to think and develop.
Yeah.
What are the considerations that has to be made?
Yeah. So I will. I have already talked to them that we will create iMac design here. So that.
Yes. So not may not be for a particular taking an example.
Yeah.
That because some basic principles are same actually.
Yeah.
I mean how the you think, how what are the consideration, what are the how the end users requirement is considered, how the regulatory things are considered, quality is considered, ethics is considered, ethical aesthetics are considered. So all the parameters, then step by step how you develop a proof of principle first, then a proof of concept, test your hypothesis, then go to a MVP, again coming back and raw material optimization. For example, we find that many of the startups are developing a prototype by 3D print, right? But for mass production, when they used to go for an injection molding, the entire things got changed.
Yeah.
Again, you have to. So all these things has to be considered. So,
I will come to that.
all these things can be much more discussed, interactive discussion.
Yeah. Sure.
So let's go. सर नाश्ता करें तो अपने यहाँ लंच स्पेस तो क्या क्या हो सकता है? You have a phenomenal level of experience from biodiesel manufacturing to creating feeders. Like what? How do you like how are you contacted? Like are you people contact you because they know your reputation and all that, or like you have a company or something? Yeah, I have a consultancy from
But then I started that consultancy from 4 years back. Earlier I was employed here and helping people. So that is how.
It's very inspiring actually. You have asked us to the phone number that you have.
Yes.
We are working and certainly we are very candidates going to see
Come to our this thing, our bakery. I can take it. 989339679. 98933. 967. Narendra Patel.
we want to the coordinated thing that you told.
Yes.
So I was thinking of conversation. We can keep it there. We will have this room set up where we can. Or we can have journalists, or and then do some kind of lighting, some kind of whatever, some kind of keep the select.
At present, they are using Lutetium 177.
Habitation. But because I don't want to go to BRC, then I was thinking someone nearby.
Come to our this is bakery. We are always there to help.
मेरे डायरी वो फाइल जो है बहुत बहुत कम आते भाई फिर तो अपना रिज्यूमे के अपना प्रोजेक्ट डिटेल्स रखने के लिए सबको वो करने के लिए बहुत मस्त लगता है।
मैं एक चार्टनेस की एक मेरी खुद की ऐसे बनाने वाला बुलाओ ना
क्या लाओ
हो रही मेरी है
तो दो ना हाँ तो उसमें मतलब being a professional you have to be check out your workflow okay understand that's it.
सर की है ना सर की भी
हाँ
यूट्यूब
case study. Means any of you wanted to discuss this thing, particular case, or maybe we can take the case of IMEC. So that we can take, or maybe we can, let us start with this glass. We wanted to create this glass. So what consideration you should take? And nowadays, for making this, particularly suppose you want to make this glass from this thing by 3D printing. So in 3D printing nowadays you can create the model, and by just giving the command you can get it printed. So that is one way. But then the material of construction will be plastic that you choose for the 3D printing. And nowadays 3D printing machines are coming with very good surface finish and all, but then they are little expensive. Normally the 3D printed job has poor strength and the poor surface finish. So that is the disadvantage. But then for your this thing device idea, you can get the roughly idea that after making this device, my job will, anything object will look like this. So that idea you can get with the help of 3D printing. But then 3D printing is the upcoming and nowadays more in practice. For small quantity production, people use 3D printing machines. And then after other options, if we are talking 3D printing means mostly it is plastic material. 3D printing cannot be used in glass. Nowadays even metallic 3D printers are also coming. But then metallic reactive 3D printing and metallic 3D printing is it is still in a research level, or maybe not. It is not much there is no much installation in India. At least in India, I heard there is one installation in Bombay. Otherwise, there is no such installation. And means even metallic 3D printers are also coming. So other alternatives, like we are talking about the plastic this thing. So in plastic there are many options are available for creating such this thing body. So first and most easy is FRP. FRP is basically fiber reinforced plastic, or there is a GFRP and CFRP. Two things are coming. So GFRP is basically glass fiber reinforced plastic, and CFRP is a carbon fiber reinforced plastic, and we can create this object from both this thing material. In FRP molding, there are I think it is the most easy way of creating any object. So normally what they do is, if you want to create this object from the FRP, then they take this thing object, and then on the surface they apply some this thing wax. So wax layer is basically to separate the mold from the object. So that is the practice. So then they apply some wax, and then after applying wax, they apply the glass fiber layer, and then pour this thing plastic resin on it. So on glass fiber, the plastic resin sticks, and it creates the mold for this object. And then by just pressing, or maybe you can take this glass away, and that becomes the glass fiber will becomes mold for you. And then now if you can create the mold, then most easy way, apply this thing wax layer, and then apply this in glass fiber and pour it this thing with resin, and you can create this object with the help of this thing glass fiber reinforced plastic. Same thing, you can use carbon fiber instead of glass fiber. You can use carbon fiber. So carbon fiber is much lighter, and this thing it has a strength maybe higher than steel. This thing carbon fiber has a strength. Yeah, it is a 6 times lighter, and maybe 2 to 3 times higher. It is having 2 to 3 times higher strength than steel. That is why this thing for CNG nowadays this thing carbon fiber reinforced plastic tanks are come. So it is a very light material. So that kind of material one can use. And then next is plastic. But then for plastic, you have to create dye. Maybe you are this thing for any injection molding or maybe any this thing production work. One has to create the dye, and for that you have to create the this thing negative means inside mold means punch the outside mold, and then inject the material into it with some this thing extruder, and at some with some force. So that is how you create the plastic object. So that is the option. But then in industry, if there is a large quantity production, maybe about 10 lakh, then only you will go for dye, because dye is too costly. Plastic injection dye is too costly. And the next is plastic 3D printing that we have already discussed. And
Sir, with your permission, I just want to pause something.
Yeah.
I know that some people maybe she is from biology. So I just want to relate one thing, that whenever any prototyping is being developed, it is not, prototype is not a model that you are going to develop. That is point number one. It should be developed first. Definition of the prototype has to be it has to be defined properly. What is the definition? That what exactly this machine or these things will be delivering, to for whom it is getting delivered, and what are the other requirements. For example, something may be a portability may be a requirement. Somewhere maybe something other requirements are there. So these parameters are aligned first. So that is a clear MPP definition, or whatever you say prototype definition has to be built up. And we, in our experience, we found that majority, I will not say majority because I do not have any statistics data, but in many cases, this clear definition of the prototype is missing. Everyone is depending or relying on the technology itself, right? So if someone is telling that I am having a technology to do something, but exactly which product you are going to deliver and for whom you are going to deliver. So after it is getting defined, then it will come the raw materials. What sir is now taking care that from which raw material it is going to use. There are several raw materials, plastics, MS and all. Moreover, if it is for, say for example, for biological use or any regulated sector, then biocompatibility is another one. So what raw materials has to be used? Then question comes that how it will be developed. So now I'll leave it, and these are the procedures. And here, for example, if you, many of the biologists developing something, for example, from waste material, right? This is one of the big propositions. I'm developing something from agri waste or so. For example, who will supply the agri waste? How much you require? Whether it is available plenty in the market or plenty in the system or ecosystem that you can collect easily. Who will make the providing the supply chain, what will be your supply chain, whether that much of quantity is enough for reach the break even. All these considerations has to be done. Otherwise, it will be a model, but it will not be turned into a functional prototype. It will remain in the table only. So now to start with, this is the raw materials things that influencer material for prototyping as example suggested.
Yes, thank you, Atish sir. And basically, you are talking about user required specification, or maybe market required specification, or maybe customer required specification. Basically, whatever device or maybe whatever product uh, one is going to make, then ultimately it is eventually it is going into the market. So in some industry sector there is a practice of URS. So mostly in pharmaceutical companies. So in pharmaceutical company, they give URS to us, user required specification. Suppose they want to buy this thing heating cooling bath. So for heating cooling bath, they will give us, for example, capacity. Maybe what capacity you can supply, 2 liter, 5 liter, 10 liter. Then the next is what temperature range you can supply. So they will give you requirement. My requirement is minus 20 degree to 120 degree centigrade. So that kind of user required specification feedback one can take from the this thing buyer, or maybe if someone is this thing choosing the product where there is no possibility of user required specification comes, but then uh, one can take the this thing feedback or maybe inspiration from the this thing similar products available into the market. So that is also means process in development of a product. So that is also possible. So it means URS or means user required specification, market required or customer required specification one has to consider. Now, if we enter into the case study, for example, just take the example of heating cooling bath and capacity one can build. One can build 1 liter, 2 liter, 5 liter, 10 liter, any. So that is the engineering part. But then minus 20 degree to 120 degree. So first question will come: what fluid are you going to use? Because if you use water, then water will freeze at 0 degree centigrade and it cannot go above 100 degree centigrade. So I think you may be using in microbiology or biology, you may be using heating cooling bath, but then they use ethylene glycol. So that is why they use the circulation fluid they use is ethylene glycol. So that kind of this thing consideration comes after once you get the user required specification, like that. Yeah. So maybe I was in this thing. I have a company called Ignis Technology Private Limited in Wagodia, and we are making pharma machinery like dry bath, water bath, oil bath, and then oven, incubator, BOD incubator, sterilizer. So I was dealing with one of the a company called Baxter. So normally the BOD incubator comes with the range 5 degree to 70 degree. This is the normal temperature range comes in this in standard BOD incubators. And material of construction should be inside of the body, it should be SS316, outside the body SS4304. That is the standard requirement of the company. But then Baxter came with the idea that they want to have a BOD incubator, and its temperature range should be from 5 degrees centigrade to 120 degrees centigrade. So for that means I have to make BOD incubator same as that, but then for insulation, I cannot use this thing normally up to 70 degree one can use puff material, polyurethane foam material. So polyurethane foam can withstand up to 90 degree centigrade. So in 5 degree to 70 degree, if I use polyurethane foam, that is acceptable. But then if I go above 90 degree up to maybe 100 or 120, polyurethane foam cannot be used. So there I have to go for glass wool. So glass wool can withstand up to 800 or maybe 1000 degrees centigrade. And glass wool can offer same kind of thermal insulation like the polyurethane foam offers. So that is how I make this thing product. So while this thing making the product, one has to consider such parameters and take such parameters into the consideration. Yeah. So maybe any one of you have any doubt or any.
Next part, maybe, sir, if you can, this is one is a methods and one is a source material, then other parameters is that reliability and performance, and
Yeah.
these parameters has to be matched because the prototype, which it actually means that which will come to the market for a test marketing. So reliability, specificity, accuracy, and also the certification requirement that is optional, that is maybe in the later part of the developmental phase, but reliability testing has to be done.
Yes,
And I will request of all of you to kindly follow that TRL scale where these things are actually described, at which stage that reliability testing has to be done and all. This is and now.
Yeah, in my earlier session, I had talked about this thing aesthetics. So one aspect is aesthetic. So that we have talked, and the design and about look we have discussed. And the next comes testing. Now anything means manufactures the machine, then buyer buy the machine, but then who will ensure that the manufacturer is giving right material? So, and buyer will always buyer will always ask that means some third party should be there who can certify that the material which he is supplying is matching with the requirement. So the testing parts comes there. In this thing, if any machine one makes, then there should be some kind of test methods, like in this thing, heating cooling bath, maybe temperature accuracy. So the range one claim, so that must be tested. Maybe temperature accuracy. Plus minus any means user can ask, I require plus or minus 0.5 degrees centigrade, not more than is acceptable. So there should be some third party who can test and certify that this machine is working in accuracy of plus or minus 0.5 degree or plus or minus 0.1 degree, like that. So one part is testing. Like in I was in laser and photonics industry. So in laser and photonics industry, till date there is I have not heard there is any lab who is doing testing of laser or cosmetic products. So and all the testing meters and everything, it was available in foreign country, maybe abroad. So we were putting some practice that every year we used to buy the testing equipments, and for 1 year validity. So we were having internal testing this thing facility in our company. So we used to test our laser, like if I claim that my laser will deliver 5 watt photonic this thing energy, then I test and certify internally that my machine is delivering 5 watt. Then its wavelength is 810 nanometer. So I should have some kind of measuring equipment which can measure its wavelength, and that is how I can certify that it is giving 810 nanometers.
So here I want to draw your attention to compare the take-home message is that when we perform any research work, right? So what we used to do, we used to do, okay, fine, I'm showing that this is the result, right? And to prove it, we used to set up a assay for 3-4 methods, right? So first we go a cell-based assay, then again qPCR, and then a protein, and so 3-4 methods. These are very much method centric to define or to prove that my experiment is fine. But when the production things comes, the experiments are set up for 2-3 purpose only. It is for the claim, what you are claiming, and what your customer wants. That's all. No extra, because these are the take-home message, because we find that many of the cases are like this, especially those who are having a deep background of academic research. So no, go for a flow cytometry, then go for this and that. But we do not consider actually what is the value proposition and exactly what experiment has to be done. Otherwise, it is not required. So everything is required for proving the reliability, and even before the third party testing, right? So this is one. And the second point where the methods and the testing things are considered, that is the statutory requirements. In biomedical sectors, for example, if it is a medical device, then possibly CDSCO have given some guidelines of how much number of sample size would be there and what would be the requirement and all these things. So these 2-3 points, based on the requirement only, the experiment has to be set up. It is not all an experiment to reach things. Secondly, when I'm just this statement I have just related to other aspects also, because it is also learning to a development and designing the prototype only. But for more direct intervention in this part, that whenever, just I forgot to mention earlier, whenever one has to select the material or methods, what methods I'm going to do, whether I'm going to do for a 3D printing, or usually 3D printing is a user-friendly method for small-scale production. But we had to all variables we have to keep in mind that for large-scale production we won't be able to produce by 3D print. So what will be our consideration of whether this material will also be used for, can also be used for the other methods like molding and all be used, or what are the type of iteration we have to make, because one iteration will not solve. I can show you a demo prototype that has been, looks like a final, that one of our startups have built up device that is a 3D printed. But when that startup has to produce a number of these things, it cannot be 3D printed. So again, that mold has to be, so the design has to be compatible design. The material has to be a compatible material. So all these parameters has to be considered.
Yeah. And Atish sir talk about the regulatory. Like if one is dealing with medical device, then in medical device, the regulatory body is CE certification. So in our case also there was a CE certification. So CE certification was in two parts. One is the overall build quality of the machine, then user interface of the machine. That was considered into the this thing machine part, and then the part means the which was in coming in contact with the human body. So that part is regulated by this thing CDSU.
Yes, actually, just to clear, CE is a quality control authority and CDSCO is a regulatory authority per se. So for any sorts of medical device, CDSCO ultimately approval is required at different phase for trial, testing and production. Whereas CE is the body that can, it's not only for medical device, in fact, it is for all electronic equipment and it certifies that these electronic equipments are as per the industry standards. That is the purpose. Purposes are both different.
And for particular in this thing medical device, there is one standard called 13485. So 13485 is a standard for medical device, meant for medical device. CE is a very generalized standard and it deals with the EMI, EMC, RF. So means one has to test the machine whether there is any electromagnetic interference outside electromagnetic interference is affecting to the machine, or whether machine is creating any electromagnetic interference and emitting and means that radiation is emitting into the surrounding. That sort of control and that sort of testing and everything falls under the definition of C, like that. Yeah, means this talks about the testing and all, and we have talked about the aesthetic, regulatory and everything. Now, if anybody has this thing, any doubt or anything, then we can discuss or maybe we can conclude it.
Do you have any your own product that you want to build up or you want to develop? You can take it for any. But many of them are not directly from material engineering.
Yeah.
I think IT or chemical engineering or biology is majorly that. So the basic principle that the purpose of this session was just to be engaged in a case studies and the case histories and the experience sharing and the discussion. But we will come up in the last time also we have discussed that we will come up in the theoretical aspects of it, how to build up in the coming sessions, and we will go. That will not be restricted for any particular domain. It will be generalized for making this. Okay. Yeah, please. Yeah, please.
It's okay. So, the question I wanted to ask is, you've built a lot of products and you must have prototyped for them as well. So, what kind of shift occurs when you are prototyping for scientific validation or for market validation? So, what is the difference between when you are prototyping for market validation or scientific validation? How do you approach the differences basically?
No, scientific validation means just like I made this thing biodiesel. So that validation means benchtop verification I carried with the help of few reactants and glass apparatus. So that kind of scientific verification, suppose I want to create a dry bath. So what I will consider means dry block heater. So I will take aluminium block and then drill a hole into it, and then measure mass weight of the same, and then I will calculate that this is the 1.3 kg of mass is aluminium block, and if I want to raise its temperature from 35 degree to 80 degree or maybe 90 degree, so I will require 700 watt of heater. So I will connect 700 watt heater and everything, and then I will test. But then I will for scientific testing or maybe POC, proof of concept, whether I can raise the temperature with this heater up to 100 or so. So for that I don't require any enclosure. So I will not bother about it. And for that I will not bother about EMI, EMC compliance. I will just test proof of concept. Take the block, drill, and then attach with heater and with controller and everything. Just everything by just placing on a bench, and I can test my idea. That is how I will means apply my science and test it. But then while going for CE, then I have to go for EMI, EMC, RF, everything. Then in CE, there is a standard, means your enclosure should not have opening where you can pierce your fingers. So I have to consider while placing this thing perforation or anything, so that perforation should not be large enough so that anybody can this thing like that.
I want to add over here because possibly most important, one of the example already he has given that when he reached to with some device to a beautician, someone have accepted that crude aesthetics, but beauticians didn't accept it. What is the purpose? Uh, Here also there is a phase where what you were telling, that is a market validation. First, that is where that scientific terminology is made, that a MVP has to be developed. That is a minimum viable product. Viable means that your working principle is, as per your claim, is it is a viable. Now you give it to the market in a limited number of market, and you take the feedback from them. Then again you may need to validate it, revalidate it with their requirement, because you find that some doctors are okay with that, some doctors are not okay with that. So that is the phase where market validation has to be done, and you have to take some focus group type of approach to take some feedback in. So here 2 points of validation. So actually not three parts. One is a scientific validation, as you were telling. Then another is a required specification. Based on that validation, what the regulator see and
proof
things.
of concept revision 1, proof of concept revision 2.
2, 3, 4, and this one. Then
final
it
product.
lands to a final product. That is sometimes it termed as a minimum marketable product or most lovable product or so. So this more the theoretical and logical strategic work you do at the beginning, you need less amount of iteration, less number of iteration, and that will reduce the ultimate effort, cost, time, and all. So, is there any other question? Yeah, please.
So till now you have taught us that this machinery things like prototyping about that. So I want to ask you the products which are involving the life systems such as fermented foods, pharmaceutical products, agricultural products which are involving the live bacteria or the life system. They are used in the product. So what to consider, or what are some major points for developing such types of product? What are the things we have to take care while developing the prototype for these things? Can you throw some?
Actually, I am not from the life science or maybe biology background. So, but then
I'm basically from biology. So it's a very interesting question.
Yes.
So the basic principle is very simple. First, you define your value proposition, and how the last day you will learn, right? What is the value proposition? What you claim to deliver? The same logic, and what the user requires. For example, you take the example of your kids. Right now you can tell me one what is the product?
So that potash fertilizer with
Yeah,
the
oil.
use of live organism, and which can what I have faced till now, that it might happen that robust technology will robust like that term can be over. I have to overcome. like depending upon the environment or depending upon the soil condition, depending upon the situation, my organism have to compete the seasons. My organism have to
So
compete
one
with
point
the
is
soil.
robustness.
Yes. So how to deal with
One
this?
point is robustness. Another.
Yes.
This is the only channel. What are the
Yeah,
requirements?
this is just the
If
ideation,
it
so I
is,
don't know what are the other.
if it is that robust, the robustness is the only factor that you have to handle. The next phase is that what are the parameters for this robustness, right? So it has to be a defined parameter. It is not an endless, right? Robust, what does it exactly means? It is a variable temperature. It should act in a variable temperature, or it should act in a variable soil condition, or it should act in a variable weather condition. What are the parameters? And now you simulate the parameters. Where you are going to apply. I mean, you cannot target a n number. So, what is your primary target customers group? Primary customer group to whom and where, which location they are going to do, for which crop they are going to use. It is also a crop specific. After having clarity of all this parameter, you simulate what are the parameters to be studied, and what are the minimum parameter to be studied, and what are the optimum parameter to be studied, and what phase wise. So once you see that all these parameters are matching, that is your prototype definition. That's all. Right? And quantity is also one. So that is your prototype definition. So for example, if you see, okay, my product should, my organism should keep alive for for this many days, or this many in this many of conditions. And if you miss out any of these, it is actually not serving your prototype. But first you have to define accordingly, because this doesn't have any thumb rule. You have to define what will be your prototype. Accordingly you build up. So next the other parts will be similarly. So this is one part I'm talking about. Then other success factors has to also to be considered, because what will be the shelf life, how, in which format it will be, what will be the user's specification. Here also the same logic is coming. Whether the user will have wants to have it in a liquid form, or it is in a lyophilized form, or what will be the. So all this parameter has to be reduced. So this is a matter of a project to project. Actually, this will solve much in a project to project discussion only. We can continue at any time. pH can be another. I mean, it depends for many parameters. So it varies from project to project, and all other the actual topic should be how to build up an innovation proposal. So on that, everything will be theoretically covered. In coming days, we are also planning. Thank you.
I just have one more last question.
Please.
Is this that in the biodiesel plant you used the tanks from Alang shipbuilding yard?
Yeah.
So what I want to know is how do you decide for something that you can retrofit, like you can use used things? How do you decide, and what parameters do you keep in mind that for this product I can use a old thing?
Material of construction of the tanks, then capacity. I wanted to build 200 liter capacity biodiesel plant. So for that I have chosen the diameter and height of the tanks there. So that I considered. Then as such in biodiesel manufacturing plant, there is no any pressure reactor. So normally I was okay with the kind of 1.5 or 2 mm thickness of the material. So material thickness, then grade of the material, and then capacity. So those parameter I considered, and then got the old tanks, used tank there, and as such in SS 316, it's a medical grade steel. So it never corrode and never react with anything. And I got the material and then sandblasted. So in sandblasting, the upper layer are removed, and then I can always use that material. So that is how I created this thing biodiesel.
Based on specifications. Like, but is this the only case where you use something old, or like is this a like recurring thing that you do? Like,
No, I always try to reduce the cost. Like in sputtering machine, normally in sputtering machine, people buy this thing power supply, high voltage power supply. But then means I used transformer of microwave, and just by rectification I could create 3000 volt, and it costed me around 1500 rupees. So in 1500, maybe 2000 rupees, I made this thing sputtering machine. So I always try to reduce the cost. Even this thing first in the MS University was I presented that small furnace, 50 mm thick and 100 millimeter dia furnace. So when I was making furnace, there was a limit. Means one limitation, I cannot use iron, maybe in the form of steel also. So I chose the material aluminum. And then there was a limitation, means I have to take electrical connection from outside up to heater, or maybe a sensor connection from outside to the this thing sample holder. So there was a limitation, means how I can take the electrical wires from outside to inside. Then means normally they use ceramic feed through. Basically, ceramic feed through is a cylindrical tube, and outside there is a threading, and inside they pass the ceramic, and inside the ceramic there is a conductor. So that is how you can take connection from outside to inside. Now I inquire at Morgan Ceramic, and there is a ceramic company called Ceramtech. So their minimum order quantity was 100, and minimum order value was for 4 lakh rupees. Now my project budget was very narrow, and how can I buy this thing ceramic field through of 4 lakh rupees? So what I did, I took spark plug. Spark plug is basically ceramic feed through. Outside there is a thread, there is a porcelain, and then in the center of porcelain there is a conductor. So I used for this thing spark plug. I drilled the hole on the surface of furnace and fitted the spark plug, and then that is how I took the connection. And I make this thing, always try to make project low budget, because at the time of research, or maybe you have to bring this thing funding from anywhere in university, or maybe any NSC project. In our case, it was Nuclear Science Center who was funding us. So for everything and anything, I have to go to them and say that I want this, I want this. So, and based on the availability of material, this thing funds they give us. So
basically, you are like, because of your trial to reduce cost every time, you get alternative methods and cheaper methods.
yes. Yeah, I can tell you one case, that case of this thing, tray, microwave friendly tray making. So I created mold, I bought the heater, and I made this thing homemade thermoforming machine. But then for thermoforming, I need this thing vacuum pump. So, and it was very small tray. What do you think? What I did? But just by mouth sucking, I was able to create those discs. So instead of vacuum pump, I was just by mouth sucking. I had created those 100 discs and supply it to this thing buyer. So then after when I get the order, or maybe when I get the advance from the party, then I can start making, or I can buy vacuum pump.
Okay, thank you, sir. Thank you all. Just we'll have a group photograph downstairs.
transmission